So of the three questions here, I mean, they're all important, but number 3 is really our ultimate goal. We want to be able to factor large degreed polynomials. That's our overall goal with this. You think, get back to the sketching, we need to find the factors so we can create the charts, figure out where to sketch it. We learned a bunch of tools to go through, and one of the important ones helps us look for the right roots was called Descartes' rule of signs. What it tells us, because that's what it says, doesn't say use it yet, or we will practice using it, just says to explain it. Descartes' rule of signs tells us how many zeros we should have on the left side and the right side. So the positive x-axis and the negative x-axis. So I copied these straight out of the notes. It says the number of positive real zeros, or right side, is either equal to the number of variation in signs of p of x, or is less than that by an even whole number. This part probably doesn't make much sense when you first learn it, but what we're accounting for by this statement right here, this less than by an even whole number, we're accounting for that all of these zeros don't have to be real. They can be complex. And that's where we go with this week, okay? But what this is telling me is it says if I am on a coordinate plane, positive zeros are on this side. It's telling me how many of the numbers, how many places that across the x-axis should be positive. The negative ones are over here. It's telling me where, when I look over here, how many I should look there. Because remember, we get our P over Q list from the rational zeros theorem, and it can have positive values and it can have negative values. If you're searching for 4 roots and 3 of them have to be positive, what type of numbers should you start with? Should you start with the positives or the negatives? I would start with the positives if I was looking, because I have more chance. There's 3 of them on the right side, 1 of them on the left. 3 of them are positive, 1 of them is negative. Means that if I start testing with my positive numbers, I have a higher probability of finding one because there's more of them on that side. That's really the idea with this. So let's look at the first part. So P of x is saying your polynomial. It's counting sign changes. So you got to look at each independent term in here and determine whether it's positive or negative. So 4x to the 5th that's positive. What's the next one? That's negative 18. That's negative. That's negative. That's positive. I don't care about the number. That's kind of why I write it below it. But what we're counting is when we go from one to the other. So there's one sign change. Negative to negative is not a sign change. Negative to positive is another. Positive to negative, that's another sign change. And then negative to positive. So we have 1, 2, 3, 4 sign changes. So what this theorem states is since I saw 4 sign changes here, that means my count of positive zeros could be 4. Or it could be less than that by an even whole number. What are even whole numbers? Even whole numbers are 2, 4, 6, 8, so on and so forth. So what is 4 minus 2? That's 2. What's 2 minus 2? That's 0. And what we're accounting for here, and what we'll see later on today, is that polynomials can have what are called complex roots, which means that the number will be complex, like we talked about in the beginning of the year. And they always come in pairs. So we're accounting for those things, okay? But right now, I haven't given you any complex zeros, so we should see 4 for this one on the right side. All right, let's go down and find the negative zeros. So this is the one that will mess people up, because this is where we have to plug in a negative for x. So this is P of negative x. So what happens is all the x's get a negative symbol in front of them. And what we have to do is we have to figure out is that still going to be positive or is that still going to be negative? And this has to do with the power like it has so many times. If you take an odd number, if you take a negative number to an odd power, do you get a negative or a positive out of it? You get a negative, meaning what's happening here and what we need to adjust for. -1 to the third. Well, that's -1 times -1 times -1. That's going to be negative. Odd powers give you negative answers. They'll turn that sign negative. But if we take anything to an even power, let's say 4. Well, that's -1 times -1 times -1 times -1. 2 negatives make a positive. This comes out as positive. Even powers always give you positive results. So anything to an even power is going to stay with its sign, meaning it's not going to change. So we look at this with the rule of signs. We look at this negative x. If the power is odd, the sign will change for that term because we're adding a -1 to it. If we have an even power, it won't change the sign and it'll stay the same. That's what happens when you plug the negative x in. So when we work through here, since this is odd, that means that 4x, that's not going to be positive anymore. That's going to simplify to -4x to the 5th. So that means the first sign is negative. Does it change the sign of this thing? Nope, because this one's even. So this one stays negative because it's negative. This will change because that's an odd. So this -6 will be positive. That's even, so that stays. It was positive to start with. Is there a power on this? There's one written, but there should be a 1 up there. Is 1 even or odd? 1 is odd. So that's going to switch the sign of this thing. So it was negative before. Now it's going to be positive, and nothing ever affects the constant term. So if we go through and we count, we only see 1 sign change right in here. So that means our negative zeros, number of negative zeros we have is 1. Is there an or for this statement? Because why not? Because I'm going to say it out loud just so everybody hears it. What's 1 minus 2? It's -1, right? And you got to remember what we're doing here. We're counting how many times it crosses the x-axis. Can you cross the x-axis negative times? No, you're counting it, so you got to physically have it. You either have 2, you have 3, you have 4, you have none, but you can't have less than none. It just means it doesn't do it. So these are the answers that we were looking for that. I didn't give you that problem on the front sheet, but I definitely thought we wanted to talk about it. So what we're also supposed to gather through this with this observation. There's 4 positives at most, right? And we hadn't conquered complex, so we should see it cross 4 times over there. That means when I do if I had to factor this polynomial, I do want to plug in my positive numbers and test them before I get to my negative numbers, all right? Let's move on. Standard form. What is standard form? This is the one, all this is this is where we got to multiply it out. Standard form is when your polynomial looks like this, all multiplied out, okay? So what we're supposed to do with this is we're supposed to use these to write the zeros. So because we have an x equals 0, x equals 3, x equals 5, x equals -3, first step we're going to do is we're going to write that in factored form, and then we're going to multiply the factors out. So we're going to do factored form first. Now remember these 4 setups right here, we got to work backwards and figure out when they're equal to 0. So this is just x equals 0. So what it means is this, since it's already equal to 0, goes into the parentheses all by itself. This one gives us the next set of parentheses right here. We've got to solve this for equal to 0, so we'll minus the 3 to the other side. And that means x minus 3 was what we saw inside the parentheses. We'll repeat that for the last 2. We'll minus the 5. And this goes in here. And then we'll add that 3. And that gives us the x plus 3. So this isn't standard form. This is factored form. Because to get that, we'd have to factor the standard form, but it shows us all 4 of the factors laid out. To get to standard form, you just need to multiply stuff out. I would pick pairs and multiply them out into quadratics and then draw the box from there. So x times both of these is going to give us x squared minus 3x. We multiply these together. We're going to get x squared minus 2x minus 15. And then one more set of multiplication. When you get to the bigger ones, box would probably pay dividends. So you could write your answer out here because we're just multiplying polynomials. So let's put the x squared over here, the minus 3x. X squared minus 2x minus 15. So let's see. Let's change colors. Fill in the inside. We get x to the 4th minus 2x to the 3rd minus 15x squared minus 3x to the 3rd plus 6x squared, and this is 45x. So our answer, multiply it all out, we get x to the 4th. Put those 2 together because they have the same variable in same variable in power. So minus 5x to the 5th minus 9x squared when we combine this diagonal, and there's nothing here. We get 45x. And this is what I wanted you guys to get to. This is the standard form. Just going backwards from the process that we're learning. Right now we're learning going from standard form to the zeros and the factored form. This is just going the opposite way. You work everything in reverse. It's like an inverse operation, okay? And this one doesn't require anything special at this point. Once you get it to this, you learned all this multiplication stuff back in probably 8th grade. Just take your time, actually draw your boxes. It'll pay off when we get into the complex stuff, I promise. -5 to the 3rd power. You're right. Yeah, my 3 didn't come out very well, did it? I see what you're saying. Yes, that 3 does awfully look a lot like a 5, doesn't it? I should be neater because I'm going to tell you guys to be neater when you write stuff out. Good call. Okay, let's do the last one. So the last one is kind of everything all together. This is everything from last week and all in one problem. So, and even before that. So what this says is, given this polynomial, I want to know how many zeros it should have. I want to know the possible rational zeros, the number of positive zeros, the number of negative zeros. And then I want you to factor it and tell me what they are. So really just kind of getting all this information into a concise pile. So let's talk about the first part. Possible zeros. Because there's a whole lot of word possible in here, right? So possible zeros. What I mean by this is how many zeros should this have based on its leading coefficient? Meaning how many times do we suspect this should cross the x-axis just by looking at it? And so we look at the the lead term. I'm asking you what that tells you. What does that power of 5 being the biggest power or the degree of this polynomial tell us? That it should have. And what I'm asking you with this one, this is based on the degree. Looking at the degree of the polynomial, how many times do we think this should cross the x-axis? How many roots will it have? Possible rational zeros. The key word in here to tip you off of this is the word rational. We know how to find where it should cross the x-axis at a rational by using the rational zeros theorem. So for this one, this number 2, I'll number them as we go down. So this is what I want you to find here is this is the P over Q list. That's the places that it should cross the x-axis that are rational. That's our factors of our last number divided by factors of our first number. So number 2 is asking you to use the rational zeros theorem. So our P value is 9 and our Q value is 4. So we need the factors of those things. Remember, they get a plus or minus with them. So factors of 9 are 1 and 9 and 3 and 3. So our P list for this is plus or minus 1, plus or minus 3, and plus or minus 9. Q is 4. So we need the factors of 4. So that's plus or minus 1, 2 and 2, and then there's the 4. And this answer is coming from what happens when we list all of these things together. Remember, P becomes the numerator. Q is the denominator, and we make fractions out of all of this. I like to start in the top, move the top number, meaning I'm going to start with this 1 over 1. So the first one we get is plus or minus 1 over 1. Let me put my green highlight down here. And then I'm gonna move this one. Then 1 over 2. Then 1 over 4. That one gave me 3 fractions. Then I start over. That one goes to 3. That one goes back to 1. Plus or minus 3 over 1. Plus or minus 3 over 2. So minus 3 over 4. And we'll do a different numerator. So plus or minus 9 over 1. Plus or minus 9 over 2. And plus or minus 9 over 4. So we just need to make sure there's none that repeat and clean up the list. So there are no repeats in that one, are there? Nope. Sometimes there will be when you get things like 4 over 2, you already have the 2 in there. So you don't need to list it twice. So just make sure every number is unique. And any fraction you can get rid of easily without listing a decimal is probably worth it. So I'm going to list, that's plus or minus 1. And we have 1/2 and 1/4. Three over 1 is 3. 3/2 and 3/4. Those are both unique. And then the 9. 9 over 2. 9 over 4. How many possible rational zeros are in that list? Is it 12? No, it's more than 12, right? Because each one of those numbers can be positive and it can be negative. So this is actually a list of, I'm sorry, not 12, 9. I went one too far. Actually a list of 18 numbers, not 9. Okay, because each one can take on a positive value or a negative value. Why do we list it with a plus or minus? So it doesn't jump into a list that's half a page long. We try to condense it as much as possible. But we do also get some pretty interesting information from this. If you look, the biggest number we have in this list is 9, meaning that it shouldn't, if it's the last rational zero I should be able to see is at 9. Most of the time that's going to be the last time it crosses, except in some extreme rare cases, could be out there at the 9, meaning you could potentially look at the graph of this thing, which is what we're going to do next, to help aid us in some of our guessing, because doing 18 divisions to try to find this can get tough. Now, this is the same polynomial that I did this stuff for, because that's what the next asks us. It asks us possible zero, how many positive zeros and how many negative zeros. So I'm going to copy that here. This is 3 and 4. 3 and 4. So 3 was positive zeros, and we've already done the work for that. We saw that was 4 or 2 or 0. And number 4 was the negative zeros. We saw that was 1. Now the idea with this these are the numbers we have to start testing, and we're looking for 5 answers. There's guaranteed one of them to be negative. So what's a better odd? 1 out of 9 or 4 out of 9? I'm going with 4 out of 9, right? I got 4 chances out of 9 possibilities from my list in number 2. There's 9 positive numbers in that list. There's a possibility that 4 of them will work, rather than 1 out of all 9 negatives. So what I'm trying to say is the reason we look at this with the Scarch rule of signs is it tells us where to start with this list. Now, the other thing, we've got all this information. We also have great technology to aid us in this because we're going to extend upon this, okay? So when we look forward, is there an easy way to see where this thing actually crosses? You guys have computers. How could you easily see what this polynomial looks like? Graph it. Only thing that I really care about is where it crosses the x-axis. I still have to divide it, but I could at least get an idea of good numbers to start with once I have my lists. Okay, I had this expanded out to 9 and -9, and I didn't see anything else. This is where all the action happens. Now we do have to be kind of cautious. So this one, I'm not sure, right? There's no exact number there. This is 1 in this picture. This is 3. Hey, I think I should use that one for sure. This is, it looks like it's about halfway in between that spot, but do we know exactly what it is? No. This one is halfway in there. This is a half. What I'm getting at is just by looking at the graph as well, I can get 2 decent spots to start, and then I can use other tools to work through the other ones, okay? I can start whittling this polynomial down. Now, when this bounces right here, what do we know about that? How many times does that factor end up in our polynomial? At least twice, right? Some even amount, because this thing bounces. That means it'll divide in there more than once. So we've got a good list of numbers here to start with. So let's start our synthetic division and actually factor this thing, okay? Because what we saw by looking at the graph and all these tools, it looks like this +3 is a good place to start. It also looks like this +1/2 is another good place to start. So let's start with those and do our division. So 4, -18, -6. 91, 60, and 9. Right? So there's our coefficients, -6, 91, -60, and 9. That's probably the most important part of the whole process, to make sure you get the right coefficients written down, because otherwise you could go through all 18 numbers and it would not work. So let's start with that +3, because it's not a fraction. We think it should work, and it'll also make our division smaller. So what are we looking for out of this result when we work through to factor this? We're looking for a remainder of 0 that tells us it's a factor. So synthetic division, first number comes down, we multiply 4 times 3 and we get 12. Now we add. -18 and 12 is -6. Then we move over and multiply, that's -18. So we add this down and we get -24. -24 times 3, so that's 72. And 91 minus 72. 19. It's positive. 19 times 3 is 57. We add down, we get -3. -3 times +3 is -9. We get the 0 that we wanted. Because what we have to work towards is, we got to figure out what these other ones are exactly that look a little bit tougher, that we're not sure of, okay? Because those are those fraction ones. We're going to leave those to the end, whittle this down with the easy stuff that we can see, and then we should be able to factor from there. Now, we know that 3 is in there twice. So what means, now that we found that factor, because remember, this means that x equals 3 does work, and its factored form, that's going to be x minus 3. That's in there once. Because it bounced, it should be in there again. So we're going to divide it again. Now remember, once we find a factor, we only need to work with the answer part of this. So we're going to work with 4, -6, -24, 19, and -3. So this is 12. Sorry, I multiplied again. This is 4. 4 times 3 is 12. That's going to give us +6 times 3 is 18. So that's -6. -18 gives you 1, which gives you 3. There's another 0 for a remainder, so that means it's in there again. Okay, so that means that x minus 3 is in there again, meaning we should see this factor repeated when we write it in its factored form. So we've got rid of the easy one. That's this one. Since I see it cross 3 other times, I know that that 3 isn't in there 4, because it can't take up 4 of the roots if I see the other 3. So now I got to pick another one to work with. Let's do the 1/2. Okay. So we're going to divide that +1/2 in this thing. Now again, we only need to work with the answer portion. So we get 1/2. This is 4, 6, -6, and 1 that we had left. Bring the 4 down. 4 times 1/2 is 2, which gives you 8. When you add them, 8 times 1/2 is 4, -2, -1, and we get a 0. That means that x equals 1/2 was a factor, which means we'll see 2x minus 1 in its factored form. Now at this point, once we get to here, this is where we need to be really cautious. We have 3 numbers left, meaning that we have a quadratic left, okay? We're going to factor this quadratic the same way we've always factored quadratics, because it's quick, it's direct. You guys know how to factor quadratics. A times C, draw the box, factor them, and be done. We've got a lot of numbers still left to guess with. Let's take the most direct, sophisticated route that we can. But we need to be cautious. Whenever you divide by a fraction, we need to change something about the answer, because everything was only half of what it should have been. So because I did a half, all of these numbers need to be divided by 2 as well. Meaning to write this answer out, I really should have 2, 4, and -1. There's a common factor in all those numbers. It'll happen every time you divide by a fraction. And that common factor will always be the denominator of what you divided by. Okay, synthetic division. This is also why we don't teach you synthetic division in Math 3, because it's not really supposed to be used unless A is a whole number. You can adjust your answer and make it work for the fractions, which makes life a lot easier, but you have to remember when you're done. So what that means is we're left with 2x squared minus 4, plus 4. Wait a minute, why does that not factor? Oh, I know why. Does that factor? It's a loaded question. Does it factor with the way that you would normally think of factoring? Are there any factors of 2 that will subtract and give you 4? But does that mean it doesn't factor? If you plug that into if you plug 2x squared plus 4x minus 1 into Desmos, you would see across the x-axis, meaning it has x-intercepts, which is what factors mean. And this is going to extend us into here. What this means is it's out of rational zeros. It means these other numbers that we saw right here, they're not rational numbers. They can't be represented as fractions, meaning they would have never been in that list. We could have sat and divided that list repeatedly over and over and over again and never found the answer. So if we want to find those 2 roots, there's another powerful way to factor quadratics that you have to remember. And it's written up there by the clock. You have to factor these using the quadratic formula, which we're going to be using quite extensively this week, which is what? Negative b plus or minus the square root b squared minus 4ac all over 2a. Because those roots don't have to be rational, okay? The ones that we dealt with all last week and the stuff you would see on this quiz that was Monday will be rational, but we're moving past that. So we need to plug in these numbers. So we have -4 plus or minus the square root of 4 squared minus 4 times 2 times -1, all divided by 2 times 2. So we get -4 plus or minus, let's see, that's 16 plus 8. So that's the square root of 24 over 4. It also means that we now have to deal with, can we simplify that square root? Are there any perfect squares of 24? It's a factor of 4, right? And 4 has a perfect square. So that would mean that it's -4 plus or minus 2 root 6 over 4. And that's important because if you did get one of these and they asked you about the irrationals, anytime all of this stuff has a common factor, it means we can divide it out. So they all have a 2 in common. -2 plus or minus the root 6 over 2. Those are the other 2 roots of this thing, which we can write in factored form. And we'll do it on the next slide just to see it. So we found all 3 of them. We had an x equals 3. What else did we have? We had another, I'm sorry, x. We had 2 of these. Then we had x equals 1/2. And the last one that we had was this x equals -2 plus or minus the square root of 6 over 2. That one's going to be messy. So, but let's work down. I just want this in its factored form. So that means we need to solve each one of these things for 0 and see what happens. So this one's going to be x minus 3 equals 0. So that one works just the way that we thought it would in the beginning. This one right here is also x minus 3 equals 0, because that's why we saw that bounce. So this is x minus 3. The second one, we move the 2 first, then we subtract the 1, and that is 2x minus 1. And there's a reason I put that 1/2 one in this problem as well, because it'll help us with this mess. And this is where this becomes important. How do you get rid of the 2 first? We multiply it over. And then we add that 2. Now, this is where it's important to remember, this really means 2 roots. One of them is 2x plus 2 equals the negative square root of 6. The other one is 2x plus 2 equals the positive square root of 6. So we're going to add to get that one over to make it equal to 0. And that means that this is what's in here. We're going to subtract to get that one over. And that means this one is what's in the last part. And what we're starting to see here is whether they're rational, irrational, and what we'll talk about this week's complex. What we're leading to is every polynomial will factor in to however many roots we see from the degree. Some of them just get pretty messy. Now, the reason we did this problem first, if I go from factored form to standard form, right? Meaning if I took this right here that I just highlighted in green, and I draw the boxes and I multiplied everything back out, guess what you would get? You would go right back to that polynomial we started with, right there.